Hi, everybody. My name is Daniel Kostic, and this is a joint work with Henk Regt, Bruin, Marc, Slors, and Kareem Khalifa. I'm a Radboud Excellence Initiative Fellow at the Institute for Science and Society at the Radboud University in Nijmegen, the Netherlands. And I would like to acknowledge uh, uh, generous support of the Radboud Excellence Initiative, which currently funds my research. And today I'm going to talk about understanding the relationship between structural and functional connectivity. Now, the structure in this context refers to networks of anatomical connections in the brain, also known as the structural connectivity. In structural connectivity networks, the nodes represent neural elements such as single neurons at the micro scale or neuronal populations at the macro scale. And the edges, on the other hand, represent physical connections such as axonal projections between individual neurons at the micro scale or white matter tracts or fibers between neural populations. The structural connectivity networks are spatially embedded and have some distinctive topological properties, such as small world architecture. Now, on the other hand, the function refers to various ways in which the information is transmitted in computations in the brain or to neural signal propagation in the brain. And in functional connectivity networks of the brain, nodes represent blood oxygen level dependent or signals or bold signals in fMRI imaging or EEG channels in EEG recordings, and the edges represent synchronization correlations between bold signals or EEG channels. The idea is that if two bold signals or EEG channels are synchronized, the populations of neurons that the bold signal represents or the brain areas that the EEG channel represents are connected. Now, some background of the problem with which we are starting. Neuroimaging studies provides a tremendous evidence that structural and functional connectivity are related. Now, early studies of structural and functional connectivity found that nodes that are central to the structural connectivity are also central to functional connectivity. And another important empirical fact that supports the assumption that structure could explain function was the early finding that structurally connected areas of the brain exhibit a greater functional connectivity. However, subsequent neuroimaging literature shows that even though the most functional connections are not supported by an underlying structural connection, in fact, functional connectivity is often higher in anatomically unconnected areas. Such relations can still be explained by appealing to pairwise, that is, local direct anatomical connections between functionally connected areas, and higher order interactions where the functional connectivity variability is mediated by the global topology of indirect connections. Now, based on this background, uh, these are our claims. The relationship between structural and functional connectivity in the brain is assumed to be central for understanding how the anatomical organization of the brain supports its functioning. However, we argue that such understanding is not necessary given the explanatory autonomy of structural and functional connectivity. And we define structural functional autonomy in the following way. Structural connectivity models can explain phenomena that functional connectivity models cannot, and vice versa. Now, our argument for this claim is the following. If the structural functional autonomy thesis is true, then understanding the relationship between structural and functional connectivity involves contextual perspectival knowledge about which models explain which phenomena. But knowing which models explain which phenomena does not require knowledge of how structural connectivity grounds, that is, how it determines or helps to predict functional connectivity. And thus we conclude that understanding the structural functional connectivity relation does not require knowledge of how structural connectivity grounds functional connectivity. Now, to understand this argument, we need to clarify some basic concepts. For example, what is an explanation? Now, uh, on an influential view in the philosophy of science, propagated by James Woodward, shown here in the picture, uh, explanations are answers to why questions. Such why questions normally are about why some event rather than some other event occurs, or about why some property rather than some other property obtains. In other words, explanations are contrastive. Consequently, why questions and the answers to them distinguish explanations from mere predictions or descriptions. That is, whereas descriptions are about what is the case, the predictions are about what will be the case, and explanations are about how or why something is the case. And understanding why something is the case rather than something else is fundamentally about understanding in what ways the system would have been different had some of its properties been different than they actually are. And the questions about how a system would change in circumstances that are different from the actual state of affairs, that is, in counterfactual situations, help to uncover which dependencies hold and are relevant for our understanding of a target phenomenon. In philosophical terminology, explanations track counterfactual dependencies, and that is what distinguishes them from mere descriptions or predictions. Now, for example, an answer to a why question such as why is information processing in the brain as efficient as it is, rather than inefficient or less efficient? It is because the brain is a small world network, and had it been regular or random network, the information processing efficiency would have been lower than it actually is. Hence, explanation provides knowledge about counterfactual dependencies. Now, how is structural connectivity used in explanation? For example, when structural connectivity explains, a typical question is why are wiring costs in the human brain X instead of being higher or lower than X? Here, structural connectivity can be used as a counterfactual in the following way. Had a structural connectivity network had a random or regular topological architecture as opposed to small world, which it actually has, the varying costs would have been higher than they actually are. And the varying costs refer to the finite metabolic and physical resources required to establish or maintain neural connections. Thus, the explanation provides information about the counterfactual dependence of wiring costs on the small world topological architecture. Furthermore, the dependence between wiring costs and small world topology and structural connectivity holds in virtue of nodes and edges having distinct causal roles in the underlying anatomical structures in the brain. On the other hand, when functional connectivity uh, is used to explain, or when it explains, it is typically used to show why a certain feature of interest depends on global temporal properties of the brain. That is, topological properties of functional connectivity networks provide information about the brain's global synchrony. For example, Halling and colleagues studied patients' response to anti-epileptic drugs, and they hypothesized that such response depends on mean functional connectivity, or MFC. That is, MFC is the average strength of correlations that exist between any two nodes in a functional connectivity network. Now, the counterfactual in this case is uh, had the medication decreased rather than increased the patient's MFC, then the patient's uh, ictogenicity, or likelihood of epileptic seizure, would have been lower rather than its actual value. Now, nodes and edges in functional connectivity networks are chosen by convention. That is, they represent global temporal synchronization likelihoods between time series. And due to this, they do not have distinct causal roles as they do in the structural connectivity networks. And here lies the problem. Since An explanation in functional connectivity networks does not require knowledge about distinct causal roles of the elements of the anatomical structure. Explanation is explanatory autonomous from structural connectivity. In other words, explanation functional connectivity provides explanations of certain behaviors and properties which structural connectivity cannot, and vice versa. And structural connectivity provides explanations of certain behaviors and properties which functional connectivity cannot provide. And in conclusion, so this leads us to a conclusion that understanding a relation between two kinds of explanation in general is not simply grounding one in the other, but rather is knowing when both kinds of explanations are possible and when only one kind of explanation is possible. Thus, understanding functioning of the brain does not necessarily require how the anatomical organization of the brain supports the brain function. That is, each can be explained by different kinds of explanation, which do not have to be grounded in one another. That will be all. Thanks.